Hello everyone, this is Greg from ChemCore. In this video, we're going to be covering the VSEPR theory worksheet. If you hadn't had a chance to look at this worksheet, I really suggest going to the description below, checking that out. In the first question, we're supposed to determine the bond angle for each of the indicated central atoms. And so also you probably want to determine the hybridization for each of the highlighted atoms. I'm going to do that first. I think the hybridization is a little bit easier. Let's make this pen a little smaller. There we go. I think the hybridization is a little easier. This carbon is going to be sp2 hybridized. We have a double bond there. Each of these oxygens are exactly what they want, and so they're going to be sp3 hybridized. This one as well, also sp3 hybridized. And now all we have to do is really determine our bond angle. The easiest way to do it is kind of imagine in your head. I do have a chart that was attached to the instructional video on the VSEPR theory. If you hadn't had a chance to look at it, I really suggest you do. It's going to clear things up because I'm going to take the angles from that chart. It's really worth committing that chart to memory. An sp2 hybridized carbon like so will have a 120-degree bond angle. An sp3 hybridized oxygen will have a 109, around 109.5 degree angle. We'll just keep it at 109. The oxygen up top, it is also sp3 hybridized, but it only has one bonding region, only this double bond. And so this angle will be 180 degrees. In the next structure, we have three atoms, again, highlighted. I think it's easy to do the carbons. The carbons are each sp2 hybridized. They each have double bonds. So sp2 hybridized. That arrow, fix that arrow. And the nitrogen has three bonds, exactly what it wants, meaning that it is sp3 hybridized. And now sp2 hybridized carbons have an angle of 120 degrees. It's really easy to remember the carbon angles because they really don't change within hybridization and with the geometry. And the sp3 hybridized nitrogen will have an angle of 109, around 109.5, but around 109 degree angle because it is sp3 hybridized. The next structure has three carbons, makes it easy for us. Each of these, well, the carbon on the left is sp3 hybridized, only single bonds. Carbon in the middle is also sp3 hybridized because it only has single bonds. But the carbon all the way on the right is sp2 hybridized because of that double bond. Now the sp3 hybridized carbon is tetrahedral, meaning it is a 109 degree angle. Same thing with this carbon, sp3 hybridized, also 109 degrees. And the carbon on the right will be 120 degrees as our usual sp2 hybridized carbon. For the next problem, we are tasked with drawing the Lewis structure for each of the given molecules. We have to determine the formal charge of all the atoms in the Lewis structure, as well as the molecular geometry around the central atom and each central atom's hybridization. And so our first Lewis structure should be SO2. S sulfur is clearly going to be in the middle. There's no other way to build the structure without having sulfur in the middle. We can build sulfur with a double bond to oxygen. The clue that I use is Honk from all the way back in the day. Oxygen wants two bonds. And so we're going to give oxygen these two bonds. And now the sulfur is left with two lone pairs, which gives it, each of them, a formal charge of 0. They're all happy with their formal charge. Now this sulfur, it is linear, and so it ends up being sp hybridized. Sp hybridized, meaning that its geometry is linear. The next structure is CH3COO, meaning that, well, clearly we'll have one carbon with three hydrogens. You guys should be used to drawing these kind of structures, seeing these carbons with hydrogens now. And it's connected to another carbon. Well, somehow we end up with 4 bonds on this carbon and 2 oxygens, meaning that we maybe should give a double bond to one of the oxygens and a single bond to the other oxygens, meaning that this oxygen has a formal charge of 0, and the remaining oxygen with one bond ends up with a formal charge of -1. And that's how we get a total charge of -1 in our structure. That makes total sense. And each of these remaining carbon and hydrogens will have a formal charge of 0. Now, the interesting thing is we don't have a singular central atom, we kind of had two carbons that are central, and so I'm gonna take them both as if they're central. This carbon over here is clearly sp3 hybridized. It has only single bonds, meaning that it has a tetrahedral geometry. Tetrahedral geometry. And this carbon over here, well, it has a double bond, meaning it is sp2 hybridized. Thus, it has a trigonal planar geometry. And if you're having trouble remembering these geometries, I really suggest checking out the chart in the instructional video. It is available for everybody. There's a link to the website where I got it from. I don't steal any information. But that chart is super, super helpful just to help you visualize and understand the namings. The next structure is NF3. Now, nitrogen is a super easy and should be familiar at this point molecule to draw, or atom. It really likes 3 bonds and a lone pair. That's exactly what's going to happen here. You just cannot forget that the fluorines also have 3 lone pairs each. And now, I think every atom in this structure is very happy, and so I think it's going to have a formal charge of 0, which it should, because the total charge of NF3 is 0, and that makes sense. Now, the central atom is definitely nitrogen, and I like to consider that I guess it's happy. It has the 3 bonds that it wants, so it's sp3 hybridized. Another way to think about it is it does also have 4 regions, and my formula, sp to the power of regions minus 1, sp4 minus 1, which is sp3. It's a great way to figure that out. If you don't know what I'm talking about, check out my orbital interactions and hybridizations video. I talk about a really neat formula to determine hybridization, and it works for a lot of other things other than just carbon. Now, clearly, nitrogen, even though it is sp3 hybridized, it won't have a tetrahedral molecular geometry. It will have a tetrahedral electron geometry, but its molecular geometry kind of looks planar. It looks like a little triangle. That's exactly what it is, except it has a lone pair. So it's trigonal, pyramidal, or pyramidal. No idea how to pronounce that. The next structure is SCl4, and so we're going to have sulfur clearly in the middle. And this is, you should be careful. Sulfur is a weird atom. SCl4, the problem we're tasked with solving, is very similar to the example I provided in the instructional video on VSEPR theory. And so what it would look like, it would have these chlorines, 4 chlorines surrounding it, but sulfur is also left with 1 lone pair. And we cannot forget about our lone pairs in the chlorines, and so let's add those. And so one way you can kind of, if you're confused, well, Greg, how did you determine that sulfur looks like this? Sulfur could look like oxygen, so it could have 2 bonds. They're in the same group, so they have some similarity. But we also know sulfur 6. If you don't remember how to do that, go to my Lewis structure video. I talk about it there. Sulfur 6 is a great way to remember it. Sulfur could hold up to 6 regions. Here we only have 5, meaning that's completely doable. And so it could end up having up to 6 bonds, but each lone pair would kind of be a bond by itself. That's why it has 5 regions as it is right now. Now the central atom, well, actually, forgot about the formal charge. All of these atoms are happy. They have exactly what they want, and so they all have a formal charge of 0. And now the central atom sulfur has an interesting hybridization. It is sp3d, and this is the hybridization we have when we have 5 regions of electron space. And one easy way to remember it, you know sp, you know sp2, you know sp3, and so this is 4 regions, this is 3 regions, this is 2 regions. Now if you go up, you just add a d, and you would get 5 regions. And you can even go up to 6 regions, where you'll have sp3, d2. And so it's super easy to remember. It's not difficult. You can go up to 6 regions, and we talked about that in the video. And so this geometry would be more like seesaw. And I didn't talk about this in the video, but it's in the chart that I provided. And so if you're not familiar with this, make sure to go check that out. In the next problem, they're asking us which molecule can the molecular geometry be attributed to an sp2 hybridized central atom. Well, we can't really do this the way they're written, I suggest let's draw it out. PBr3 is going to look like this. Remember, phosphorus 5. It's a little trick I like to use, meaning it'll have 2 additional lone pairs. This is exactly how it wants it, even though, it has 5 regions, so it is an sp3d structure. This is not sp2, and so PBr3 is not valid. CH4, I mean, you guys should not have to draw this out. This is a classic sp3 hybridized carbon. So it's not sp2 hybridized, we can eliminate CH4. Now CHCl3, again, you might not have to draw this out. No matter that we change 3 of the hydrogens into chlorines, this is still sp3 hybridized. It's still only single bonds, meaning that also invalid. Now, I mean, you can guess HNO2, but let's make sense of it. Nitrogen clearly has to be in the center. And we're thinking, okay, nitrogen wants 3 bonds, but that's not quite possible here. How can we draw HNO2 to give nitrogen, well, clearly it's going to have a formal charge, but the entire molecule also needs to be neutral. Meaning that if nitrogen gets a -1 charge, then one of the oxygens maybe has a +1 charge, or maybe vice versa. I'm thinking, well, let's connect one of the oxygens by double bond, exactly what it wants. We'll have a hydrogen off to the side by single bond because that's the only way that hydrogen could be connected. And we're left with 1 bond we can give to the other oxygen. This gives this oxygen a -1 formal charge, and this nitrogen a +1 formal charge, meaning that the entire molecule is neutral. And this nitrogen is therefore sp2 hybridized. It is now sp2 hybridized, meaning that the answer is D. In the next problem, they're asking us which molecule has a nonlinear shape. Now, before I solve this, if you were to kind of just glance at it, you hopefully see the answer right away, but I'm not going to depend on that. Let's draw it out. The first answer choice is already drawn out for us, but let's just make sense of it. This inner central carbon has no lone pairs, meaning that it is completely linear. And so this is, well, not a valid answer choice. Now, water, H2O, is interesting. If you were to draw it out like they did, you wouldn't really quite make sense of it because this oxygen has lone pairs. And there's no way we can't really draw it linear, right? Because that's not really correct. These electrons want to repel each other, meaning that we'll have this bent structure. We'll have this bent structure for this water. So our answer is probably B. But let's go through the rest of the problems and make sense of it. HCl, well, we only have 2 atoms bonded to each other, meaning that it is completely 180 degrees no matter what, and so it is also linear. So this is invalid. HCN, one way that you would have to solve this is realize, well, you need to give carbon 4 bonds and nitrogen 3 bonds, and so the only way to do that is to have this triple bond between carbon and nitrogen, meaning that you have 180 degrees between carbon and nitrogen, and so this is also linear. And the last structure, we have to somehow be able to give these 2 carbons 3 bonds, and so, well, 4 bonds, and so we have to have a triple bond in the middle, meaning no lone pairs, we are completely 180 degrees, we are perfectly linear. And so our answer choice is B. The next problem is asking us to find the geometry of the carbon indicated with the arrow. Now, don't rush. You would probably think a carbon would usually be tetrahedral, and you'd be absolutely correct, but this is not a usual carbon. This is a carbon that has a positive formal charge, or a name we'll later discuss, a carbocation. Since this has a positive formal charge, it now has 3 regions of electron density. It no longer has 4 regions of electron density, meaning that it is sp2 hybridized, and therefore should be trigonal planar. Best way I can describe this, the difference, my students always confuse trigonal planar and trigonal pyramidal. Now, the way you can realize this is that trigonal planar, and I'll draw an example of a trigonal pyramidal molecule, usually nitrogen is a good example. They all kind of, you can outline a triangle. The only difference is this lone pair. And so if we have that lone pair, it's almost like It's not going to be it's more like a pyramid, while without a lone pair, it ends up being perfectly flat. And so that's just a little tidbit of information. It's why watching these videos is useful. I give little tricks. And so this answer choice should be trigonal planar. The next problem is actually asking us for a very similar idea. What geometries does the methyl cation have? And I'll just draw it out, but we just did it. It clearly does not have 4 regions. It now has 3 regions of electron density, meaning that it is sp2 hybridized and trigonal planar. The next problem is asking us which of these structures would be trigonal planar. And so the easiest way to understand this is, well, trigonal planar means that it has 3 regions of electron density. And so it should be sp2 hybridized. And easy way for me to do that is, well, let's see these structures. Let's draw them out like Lewis with lines, and let's see which one has 3 regions. I don't like these dots, these shared dots. Realize that the shared dots in between like fluorine and bromine here is really just a line. And so if we were to draw that, that's not bromine, that's boron. Made a mistake. And so if we were to draw that out, boron has no lone pairs. Fluorine has all these lone pairs, and you should already realize, hey, hold on. Like that trick that I just taught you, this kind of looks like a triangle, and it has no lone pair, meaning that it is planar. And so my answer is probably 1, but let's go through the rest and make sure. Now this oxygen is no longer water, it is now hydronium, which is pretty cool. And so what we can draw is, well, again, this kind of looks like another triangle, but it's not planar because of this lone pair. It is pyramidal, and so we can cross this out. This carbon is same story. We have these hydrogens connected to carbon, but we have this lone pair. And so this is not your usual carbon with 4 bonds. This actually has a negative formal charge, meaning it is a carb-anion. Again, kind of looks triangular, but this lone pair gives it that pyramidal shape. And the last structure, you're very usual. You should be used to seeing nitrogen as trigonal pyramidal. It's very, very common. And so you'll have this lone pair on nitrogen, all the lone pairs on fluorine. I'm not going to draw them out. But again, it kind of looks like a triangle. But because of this lone pair, it becomes like a pyramid. So this is also trigonal pyramidal. So we're left with answer choice A. The next problem is asking us for the bond angle of the COC bond in the following molecule. Now, it is important to realize what bond they're looking for. They're literally looking for this angle. And so if we were to draw this kind of like a geometry problem, we're literally looking for this angle. And you should realize that we're looking not for the angles that the carbon makes, but the angles that the oxygen makes. And so this little negative charge on this carbon is maybe going to trick you. We don't care about this carbon. We don't care about this carbon either. We care about the central oxygen because that's the atom making the angle. And so this oxygen has 2 lone pairs that are not drawn, meaning it is your usual bent structure. And a bent molecular geometry has a 109-degree angle. And so our answer is B. The next problem is a similar concept. It's asking for the bond angle of CCO. And so you should realize we're not looking at any of these angles. We're looking at the angle that this carbon makes. And so if I were to draw it, I'm ignoring the hydrogens all the way on the left because we don't care about them. We care about this angle right over here, this little arc that I drew. That's the angle we care about, which clearly is super straight. It's 180 degrees. It is perfectly linear. Why? Because this carbon is sp hybridized. And so we know it is linear and 180-degree angle. The next problem is asking for the bond angles of the bolded carbon right over here. Best way to do it, let's draw it out. Let's take the time. I'm not going to draw on the hydrogens. I'm just going to draw on the lines. And so the really interesting thing is we have a carbocation, which is a name you probably not familiar with. It's just a carbon with a positive formal charge, meaning it is triangular. It looks like a triangle with no lone pair. And what did I say about that? It is trigonal planar. And the bond angle of trigonal planar is 120 degrees. What bond angle is associated with a tetrahedral molecule? You should know this, commit it to memory. A tetrahedral molecule has a 109.5 degree angle. You should know this. This is very, very important to remember. This means that any bond that you look at, whether you compare this bond to this bond or this bond to this bond in 3D space, it is always 109.5 degrees. which is kind of the reason why carbon is so special, and we have a whole year of chemistry dedicated to it. In the next problem, we're trying to find which of these structures would have a trigonal planar shape. Now, again, of course, you should know by now, I am going to draw everything out. And so our first structure is going to be nitrogen. Remember, nitrogen likes 3 bonds. And so there's going to be carbons at the end of each, but do not forget the lone pair. And so the trick I taught you, it's going to look like a triangle, but the lone pair makes it pyramidal. It's a pyramid. And so this structure is not trigonal planar. The next, HCN, we need to somehow give nitrogen 3 bonds and carbon 4 bonds. Only way to do that would be have a triple bond, meaning that this central atom is sp hybridized. It is linear. It is not trigonal planar. You can kind of understand all of these structures just by drawing it. That's the trick, right? Pretty interesting. NH4, well, it's a positively charged nitrogen. It has a formal charge of 1, meaning it has no lone pairs but 4 bonds, and anything with 4 regions would be tetrahedral. Tetrahedral. It is tetrahedral. It's not trigonal planar. The next structure, this is where the kind of, I'm going to draw both of them. So the next two. So CH3 with a negative charge and CH3 with a positive charge. A long time ago, I really focused on the point that carbon with a positive formal charge has no lone pair, and carbon with a negative formal charge has a lone pair. And now you understand why that's important. Well, it's important for a lot of other reasons. This is one of them. Both of these kind of look triangular. Both of them kind of form a triangle outline, but only one of them is trigonal planar, the carbocation, or carbon with a positive formal charge. Why? Because of this lone pair, it becomes pyramidal. So we'll write that this is pyramidal, meaning that our answer is the positive formal charged carbon. The next problem asks us that VSEPR theory predicts an identical shape for all of the following except. Now, I don't want to imagine in my head. Let's draw it out. And so I'm just going to draw out the Lewis structure for each of them before we start discussing. And so if you were to draw out your Lewis structures, this is exactly what you should get. Nitrogen really likes 3 bonds, but it has a lone pair. Meaning, again, it kind of looks triangular, but this lone pair causes it to be trigonal pyramidal. So we're going to write trigonal pyramidal. Same thing with the next structure. This oxygen has a positive formal charge, meaning it has 3 bonds and still 1 lone pair. Again, kind of forms a triangular outline, but that lone pair causes it to be trigonal pyramidal. Now the next problem, boron. You guys honestly should memorize boron. Boron forms 3 bonds with no lone pair. This is such a common question for them to ask because you assume, sometimes you make the mistake that boron looks like nitrogen, and so you give that lone pair to boron. But no, it does not have a lone pair, meaning it has that triangular outline, but it is trigonal planar. It has no lone pair. And now this carbon with a negative charge means that it has 3 bonds and a lone pair, and so it forms this triangular outline, meaning, again, it is trigonal pyramidal. And so we clearly see 3 structures that are all trigonal pyramidal, and only one structure that's trigonal planar, and that's boron, so BH3. The next problem is asking us which one would have a trigonal planar structure. So again, let's take the time to draw them all out. I don't like the way they're written. Really similar question to the previous problem. Again, CH3 with a negative formal charge means that it has 3 bonds and a lone pair, and so it has this kind of triangular outline, but this lone pair causes it to be trigonal pyramidal. And so this is not trigonal planar. However, carbon with a positive formal charge means that it has 3 bonds and no lone pair, meaning that it is trigonal planar. And so we can decide that, okay, 2 is a valid structure. Now, NH3, it has 3 bonds and a lone pair, meaning it has this triangular outline, but this lone pair causes to be trigonal pyramidal. So this is not good. BH3, again, please just remember, boron has 3 bonds, no lone pair. Again, trigonal planar. So this is also a valid structure. And now OH3, hydronium, has that positive formal charge, meaning that oxygen has 3 bonds and a lone pair. So it has that triangular outline, but also a lone pair. So it is trigonal pyramidal. So again, invalid. And so our answers are 2 and 4. Answer choice B. The next problem is a callback to a similar problem we had before. They're asking us for the bond angle for the CCO bond in the following compound. And so realize that we're really focusing on this central carbon right over here. It doesn't matter from where we look at. We can look at this C or this C, but we're really looking at the angle that this carbon makes with any of these sides. And so I'm just going to draw, look, this angle, it's the same no matter where I look at. And so for example, if I looked at this angle, you would realize, well, it has to be, this central carbon has to be trigonal planar, meaning that it has a bond angle always of 120 degrees. This concludes the worksheet for the VSEPR theory and concludes the last worksheet for Unit 1. Again, I'd like to congratulate you with sticking to the plan. If you've watched all the videos in Unit 1, I really thank you for your help. And if you haven't done so, make sure to subscribe and like the videos and leave a comment with any, mean or positive comments, hopefully positive comments. And I'll see you in the next unit.